Okay, so now we will study a few things about growth of functions. These things will help us in our study when we will study asymptotic analysis and asymptotic notations. So before going into that, let's see a few things over here. Now let me take an example. Let me say that there is a function n square and there is a function n log n. N square is also, you can say, n into n. So intuitively you can see here that n log n is supposed to give a smaller value as compared to n square. This is supposed to be giving bigger value. So here we have taken two functions. One is n square and another is n log n with a constant value multiplied, which is 5. Now we will see how this affects our the growth of function, the graph we are going to draw between these two functions. So we checked for n, first we checked for n is equal to 2, n square is 4 and 5n log n is 10, and we plotted it. You can see in the graph over here we have plotted things. We checked for n is equal to 4, n square is 16 and 5n log n is 40. Again we plotted this over here. Similarly we calculated for n is equal to 8, 8 into 8 64 and 5n log n. So log of 8 is 3, 3 into 8 into 5 is 120. And similarly we checked for n is equal to 16. So n square, 16 square is 256 and 5n log n is 320, which I think I have plotted over here. Now when we checked for another value, say n is equal to 32, what we found that n square, 32 square is 1024, whereas 5n log n, that is log of 32 into 5, that gives a gave us a value 800. So here you can see a difference that till here the value of n square was less than 5n log n, whereas n log n is obviously a smaller, is supposed to give smaller value than n square, but because of the constant attached here, n log n was given slightly bigger values. But when we checked for n is equal to 32, what happened? That now n square and n log n are they have started showing, you can say they have now started to show their true colors. True colors in a sense that because of the constant attached to some extent for some smaller values of n, this was giving a smaller value than this. But after you keep checking for bigger and bigger values of n, and after some point, after some value of n, what will happen, that this will start giving a larger value as compared to this, and the effect of the constant value attached will be you can say in a sense removed. So here we can say that if you check from this graph, approximately somewhere around n is equal to 22, what happens, somewhere after n is equal to 22, what happens, that the value of n square becomes larger than 5n log n. You can calculate that mathematically if you want, but it happens somewhere around n is equal to 21. I have also made another graph over here, you can look at. Now this is a graph between n square and 8n log n. Same functions, only the value of constant attaches changed. Now here also it is showing similar behavior. I have written down here, I have plotted for n is equal to 8. Here you can see 64 and 192. This is giving a smaller value. 16, 256, 512. This is again giving a smaller value. 1028 and 1280. There at n is equal to 32, n square was giving a larger value than 5n log n, but here at n is equal to 32, still n square is giving you a smaller value than 8n log n, because 8 is a bigger number than 5, you know that. But when we check that n is equal to 64, what happened? N square is 4096 and this is 3072. So here also the transition it happened that 8n log n is finally giving you a smaller value as compared to n square, but the value at which it happened was different. There somewhere after 22 you will find that n square will be giving you bigger value than 5n log n, but here somewhere after around 44 you will find that okay, now n square is giving you a bigger value than A10 log n. So what I want to infer from here, obviously I think this, if you have been through basic mathematics, you must be knowing all these things. So that what I want to infer from here, which I will use in asymptotic analysis, is that the effect, you know, of this constant, I have already said you, I think before also, that you know, when we do when we compare the runtime of an algorithm, we tend to not to care much about this constants attached. What we are more careful about is this term, this variable term, that is n log n or n square, or whether it is 2 raised to the power n, that those kind of terms, and not care about this 5 or 8, because ultimately what happens when you have to compare two functions, ultimately what happens that the function with whose highest order term is n square will give you a larger value. N square will always have a larger value as compared to a function having n log n. But that may below for some smaller values of n, this may be giving a larger value than this. For some smaller values of n, this may be giving a larger value than this, but after some value of n, this will give a smaller value than this one. Now that particular value of n at which after which this will happen, the particular value of n after which the functions will start showing their true colors, that value of n may differ depending upon the constant, because when we have a 5 over here, that was around 22. When we we have an 8 over here, this is somewhere around 44. So that may depend upon the, we call it n naught. Okay, when we will be doing asymptotic analysis, we will be calling this value the value at which this will start showing, the functions will start showing what you can call as their true colors. The function, you know, where n square will be giving you a larger value than 5n log n. So that value after which these kind of transitions will happen, I will call that value as, or we will call that value as n naught. So this is what I want to convey from here, that after some value of n naught, whether it is whatever c over here is, let's say there is n square and there is c log of c n log n. Okay, so this is n square and this is c, some constant n log n. So after some value of n, okay, after some value of n where n is greater than n naught, this will be giving you a value larger than this. Now below, where c should be greater than 0, but below this value of n, that is n naught, this may not be happening. I mean, this may not be giving you a larger value of n. So that is why, because when doing asymptotic analysis or when comparing algorithms, what we care more about are for larger values of n, for bigger input size, because it is at bigger input size that the difference in the run time of the algorithm, they become very significant. Why? We have already discussed that. So it is for the bigger values of n that we are very worried about. So we will talk mostly about the behavior of the functions at the value of fn greater than n naught. So whenever I say that this function, this particular function has a higher runtime, or it is better than, when I will say that this is better than this, because this is giving a smaller value, so this is having lesser runtime, this is better. When I say that this is better than this, what I mean that this is better than this after the value of n greater than n naught, that is assumed. Okay, so this is what I want to tell here. Next we will see asymptotic analysis.